Okay, so last week where we end, or on Tuesday, I should say, where we ended was this idea of a chi-squared test. And I just wanted to give you a visual for what we were doing. So if you're following along, you don't have to run everything that we did on Tuesday. If you'll just start by library Ggplot 2, if you can run that, and then load this data MPG. If you load those two things, we won't rehash everything that we did leading up to this. But one thing I do want to do is show you how to plot this in Ggplot. So let's create, let me annotate this. So we're going to say create a data frame for car classes by year. And remember, we had used this table function. If I just highlight that little bit and click run, remember what we're looking at is these classes of cars, and then the number of vehicles that are in the data set from 1999, and the number of vehicles that are two-seaters that are in the data set from 2008. And here we can use a goodness of fit test, that's what a chi-square test is, to ask if the distribution of cars among vehicle classes from 1999 matches the distribution of number of vehicles within these car classes from 2008. And so, but to plot it in Ggplot, we need to do just a little bit of work here. So let's create an object called car classes. Remember, we can name that anything we want. And then we do the left arrow, and we're going to use the data.frame function. And what this function does is create a data frame from whatever data you give it inside the parentheses. Okay, and we're going to use the same table function. We're going to nest the table function within the data frame function. So what it should do is create a data frame from this table here. Okay, so we'll nest the table function within the data frame function, and we'll just do the MPG data frame that already exists. And I can do the $ to choose columns within there. And we're interested in the class of vehicles. And then the second bit of information from MPG that we're interested in is the year. Okay. So creating an object called car classes, it's going to be a data frame based on a table. Then that table will house MPG class information and MPG year information. Basically what's shown here. Okay. So I'm just going to run that. Notice there in our environment up here, we now have a data frame called car classes with 14 objects, observations, and 3 variables. And if we click on that, it looks great except for the headings. So when it grabbed the data from the table, it put it into long form. So it has 1999 and then below that 2008. I didn't know what to call this column. It called it variable 1 or var 1. I didn't know what to call this column. It called it var 2. And then frequency is the number of cars. And so this is probably a problem that you will encounter again, where the column names in R don't really make sense in terms of your interpretation. And so I wanted to show you how to rename columns. And so we'll just do a little annotation here, and we'll say name the columns. And we could actually say rename the columns. And the function to do that is appropriately named called names. So we can do the function call names, and we're gonna use that function to rename the columns in this data frame that we just made called car classes. Then we do the left arrow, and then we just concatenate using the C function the names of the columns that we want to have. So the first column, that was classes of cars. So we can call this anything we want. We're going to call it class. The second column, we're going to call it year. Notice I'm putting these in quotations. And so it's going to put text in there that matches exactly what I have in the quotations. Then we just do the third column, and we can call this number cars. And that's the number of cars that are belong to each class for each year. Okay. So call names, You just have to tell it the name of the data frame that you want to rename them. And then if you just give it a vector of information, in this case, a vector of classes or names, then we can run that. And when we have a look at car classes again, just by clicking on it here in the environment, notice now we have class, we have year, and we have number of cars. Okay. So now that we have that, and if I'm going too fast, please just say something or enter it in the chat. Now we can actually use this object called car classes to plot the information from this table in Ggplot. Okay. So we'll go Ggplot. Remember, that's the function we use to create plots in this Ggplot2 package. And every time you have a function, you want to open and close the parentheses. And of course, when I open that parenthesis, RStudio automatically closed it, so it's kind of helping me to code on the fly here. The first thing that we need to tell the function Ggplot, or the first argument, is what data set we want to pull data from for plotting. And in this case, it's car_classes. So we put that in there. Then we do a comma and we use AES, which stands for aesthetics. So what do we want to visually show in this plot? And within that function, we're going to open and close the parentheses. And here we're going to do class. And then we're going to do number of cars, number of cars. Now I don't have to put quotations around those because those are columns that exist within this car_underscore classes. Okay, and what we want to plot is a bar chart. And so we can do plus geom. So this is the geometry of the type of plot that we want to create. And the geometry that we want to use is a bar. And the last little bit of information that we need to give is the state. And I'm just, by the way, I'm just going to hit enter after that plus sign. And when I do that, what that does is just continue. Notice that it offset a little bit here. And it's important that you hit enter after the plus sign and not in front of the plus sign, okay? So you want to put the plus, hit enter, and then put your next grammar of the graphics that you want to overlay there, okay? So within geom bar, we're going to say the stat that we want to show is the identity, okay? And what that means is for each, it's going to put classes along the x-axis, the first thing that we gave in the aesthetics, okay? Okay, and then I'm going to add one more. So I'm going to hit enter, or I'm going to hit plus, and then I'm going to hit enter, and then we're going to do what's called Facet_grid. This is another function where it will create a different plot or a different panel within the plot for some factor. And in this case, it's going to be year. So you just do the tilde or the tilde sign and then year. Okay, so we're creating a Ggplot object based on car_classes. Where we're showing class versus the number of cars. Then we're overlaying on that using the grammar of graphics. That's what the GG stands for. We're using a geometry of bar where we use the identity of each of those rows in the car_classes data frame. And then we're overlaying the facet grid where we break that plot up into a panel for, in our case, 1999, and then a different panel for 2008, okay? So I'll just show you what this looks like. If I zoom in on this, can you see that okay on Zoom? Okay, let me move some of these windows out of the way. So what this is showing us now is, and I recognize it's kind of hard to read some of those. These are the classes of cars. These are the number of cars. And then this is for 1999, and this is for 2008. And when we're thinking about a goodness of fit test, like the chi-squared test, which is a parametric test, or the Kolmogorov-Smirnov test, the KS test, or the vodka test, as some people call it. That's a non-parametric equivalent to the chi-squared test. And I'm going to show you how to do both of those. But the idea here, what we're testing is the distribution of cars within classes in 1999, is that the same as the distribution of bars in those same classes for 2008? So if you think about the silhouette of those two, is that the same between those 2 years? And it looks similar. There's a small number of two-seaters. There's a large number of, it's hard to read what that last one is. We try and, so subcompact SUV is the last one. So they look similar, but notice there's some differences. There's a few more pickups than there are subcompacts in 2008 versus pickups and subcompacts in 1999. And so instead of using a continuous variable on the x-axis, we now have categorical variables. But we can still ask whether or not these come from the same distribution, okay? And that's what the chi-square allows us to do. Is everyone doing okay? Were you able to make that plot for those that are following along?
I had a question about the stat identity.
Yeah.
What are the other options for that? And I didn't quite get what that did, the identity thing.
Yeah, okay. So to the group, how could we learn about what other options might be? How could we make use of the internal help structure? This is a good question because it's not always apparent in Ggplot what you would search.
I have no idea. I don't think we could search stat.
Right. You can't search stat. That's very good. Does anyone know what we can search? Okay, question mark geom underscore bar. That's exactly right. So remember, with the internal help function, we can find help on functions. So ggplot is right here, is outside the parentheses. That's our function. Here, geom underscore bar, that's our function. Here, facet underscore grid, that's our function. So we can look for help at the function level and then get information about the arguments that happen or occur within that. So if we do question mark geom underscore bar, and I put that directly into the console, so I'm just going to put enter. And notice that in the help window, so it automatically goes to the help tab in this lower right window. Geom bar is the function that we're thinking about, and it tells us the package that it came from, ggplot2. And then it says bar charts, and it gives us a description of that. And then notice down here, if you want the heights of the bars to represent values in the data, use geom call instead of geom bar. Geom bar uses stat underscore count by default. That means it counts the number of cases. And so what we're having to deal with here, Natalie, is the fact that instead of just having one row for every pickup, we actually have one row for pickups, and then we tell it in the next column the number of pickups. And so we have to do this stat ident. It's telling us here that by default, it wants to go in and count those. But we have to use the stat identity, in this case, stat equals quote around identity, so that it makes the height of those bars equal to the value that was given in the number cars column. So that's the thing about R, there's always multiple ways of doing things. An alternative could have been, we could have just used geom call instead of geom underscore bar. You want to see what that looks like? You want to try it? We can code on the fly here. So what I'm going to do is I'm just going to hashtag that out. And what that means is that's not going to be interpreted as a line of code. And what we say we could use geom underscore call, open, close. Now notice we don't put anything in there. We should be able to run this. And notice we get the same plot, okay? So if geom bar and then specifying the stat equals identity is confusing in any way, just keep in mind, if you want to do column bar charts, you can use geom underscore call, okay? And you don't have to put any sort of argument in there, okay? So Natalie, thank you for asking that, because it's always good to kind of know how do you go in and get questions or help resources, and the answer is at the level of the functions, okay? You good? Okay. Everyone else okay? Cool. Okay, so now that we kind of have a
I
visual.
have another question based off of that.
Oh yeah, okay.
Sorry. In the help description, it said to use stat underscore identity and open close parentheses. Is that the same as saying stat equals identity in quotation marks?
Let's see. Okay, so
Like, how would I have gotten to know that I needed to put stat equals identity there?
Oh yeah, well, so that came from my experience, and
Okay.
and I recognize, that not everyone has spent this much time on it. If you were to Google, and by the way, we use Google quite a bit. If you were to Google, create frequency histogram in Ggplot 2, you would probably find someone that used that approach that I have.
Mhm.
Or you would find probably someone else that uses geom_call.
Mhm.
And probably the best thing to do is use whatever functions allow you to use the fewest number of keystrokes, right? And so I did it the long way, but the geom call is the short way. And I think that's what's most frustrating about R for new users is you're not coming into this with the foundation of experience. You're building that foundation. And that's what I'm here to help you do, right? And that's why I think it's important if any of you know of like a particular type of plot that you want to create, maybe in the future, maybe you don't have the data yet, but you want to create that plot. Let's talk about it. Let's hack out some code for you now to create those types of plots. And then you may come back to it and use it in the future. But yeah, the struggle, I think, early on in R is build a foundation for knowing these things. And some of it, you have to commit to memory. But I was telling a student before class, like, I don't really commit all of this to memory if I don't use it a lot. I make use of online search engines. There's such a huge user community out there in R that you're going to find the answer within the first couple of hits on Google. So, if there's something that you're not sure about, start in Ggplot, learn a little bit about the functions, but there's entire books out there that are based on just Ggplot 2. And a lot of those are free. You can find the book online, and Hadley Wickham is the author of the one that I have. And I have a copy of it in non-COVID times. It's like when people are in class, I could just pass that around. But it's available online, and if you'd like, I can send out an email with links to more on Ggplot if this is a package that you guys think you'll use. That's why I wanted to introduce it early on and keep coming back to it throughout the semester, because like my lab, when we publish papers, we use Ggplot now instead of like Sigmaplot was a proprietary software that we formerly used, but it's expensive and it's clunky and it's like always giving us problems. Ggplot, there was one person had a problem loading it, and I'm so sorry that happened, Caitlin. But we were able to figure it out in just a few minutes before class today. So anyway, I'll send around some more information on Ggplot 2 in case that's helpful, and I'm sure it will be because there's a lot going on in Ggplot. Cool. Thanks for the question. I love the back and forth, but it's annoying when I'm just talking. Although I do recognize that's the best way to learn some of this stuff when you're new to it. Okay, everyone all right with so we fit the chi-square test here to those data. Let me just show you how to do the non-parametric. So if we go back to this plot, one of the things that if you spend time with a chi-square test, one of the assumptions is that you don't have rare occurrences, but this two-seater, there's not many vehicles that are two-seaters, and those rare occurrences can cause some odd behavior. And in fact, when we ran that chi-square test, if we run that again, notice it gives us a warning. It says chi-squared approximation may be incorrect. And that's a warning that you get almost every time you run that because chi-square has a number of assumptions that we have to make. But let me just show you how to run the KS test. So we can annotate this and say non-parametric version of chi-square is KS test. And I guess I should, it's Homogorov Smirnov, okay? AKA KS test. Okay, and there's a function to run that. It's called ks.test. And notice that's in, if I go back, ks.test. Notice it's in the stats package, and that is a package that's automatically loaded into R. It's like the base package. The stats package, the base package, some of this stuff is already in the shell of R when you get it. And so you don't have to download a package to do that. It's already there. Okay, so KS test, non-parametric equivalent to the chi-square test. But when you run the KS test, what it wants is two vectors of data. It wants the distribution from your expected and then the distribution of the data from your observed. And so to do that, in our case, what we can do is we can make those. So we can, I'm just going to make a car underscore table. And I'm just going to use that same table that we made earlier, MPG $class, MPG here. But now I'm calling it car table. And if we look at car table, it's that same thing that we made earlier, okay? And then for KS test, what we can do is car underscore table, the first column, and then car underscore table, the second column. And the reason I wanted to show you this is mostly as a reminder of this indexing idea. So we talked about this early on, but it's something that we can just reinforce today. We can go into this object called car table. The brackets will represent the indexing, and then there's a comma inside those brackets. Everything before the comma represents rows in the data, and everything after the comma represents columns in the data. And so what I'm doing here is we're going to run a KS test on the first column of data, which is here. These are just names. It's not actually data. Our first column of data is 1999. And then I'm doing the second vector is car table, the second column, 2008. Okay. So this indexing is something that you'll probably use again and again, and we'll just keep reinforcing it. But all I'm doing is using the KS function and running it the vector of data from the first column and the vector of data for the second column. Okay. We could have run it on KS test and then done concatenate 2, 25, 20. We could create a vector from this first column and then a vector from the second column. But the point is, you just need 2 vectors of data to run the KS test. Okay, and if we run that, so it tells us the data that it's running it on. It gives us a D value. In this case, that's our test statistic. It gives us a P value. Notice that P value is at 1, so the probability of finding a value that's greater than D, and D is on a scale from 0 to 1, so that's pretty close to 0. And the probability of finding a value greater than that is pretty high. And what we can conclude then is, based on this KS test, is that those come from the same distribution. That the 2008, the number of cars in each class in 1999 is basically, from a statistical standpoint, the same as the number of cars in each class from 2008. Okay, which you might have guessed if we looked at these 2 silhouettes of these distributions. They look approximately the same. And when we use the KS test to do a non-parametric quantitative comparison of the 2, we can conclude that those come from the same distribution. Okay. Everyone all right with this idea of a goodness of fit test? We're just taking this idea of some of the tests that we do with continuous data, but we're doing it with categorical data. Okay, so let's just think then for a minute about, let's do a different test here. So let's test for differences. So remember, in that flow chart, there's tests of differences, and then there's tests of association. And we're still thinking about tests of differences for the moment. When we get into the regression here in a minute, we're going to be thinking about tests of association. But here, we're going to test for differences in C2Y. And remember, C2Y is city fuel economy for these cars in this database that we're dealing with. And we're going to think about among drive types. Okay, and we can visualize that pretty easily in Ggplot. Just Ggplot. We're going to use MPG, the original data that we loaded. AES, remember, is aesthetics. And here we want to show drive, comma, CTY. And I misspelled drive. That should be DRV versus CTY. And then let's just do a geometry underscore box plot. A box and whisker plot, as it's called. Okay, so for those that are following along, Ggplot, we tell it the data frame, in this case MPG. We tell it in the aesthetics function, we tell it what we want on the x-axis and then what we want on the y-axis, and then we just need to tell it the geometry of the plot that we want to create, in this case a box and whisker plot. We hit run on that. Notice now we have drive type, so four-wheel drive vehicles, front-wheel drive vehicles, rear-wheel drive vehicles, and we have city fuel economy. And then these box plots represent the median, the 75th percentile, the 25th percentile, the maximum observation, the minimum observation, and then what are statistical outliers. So the dots represent extreme values within each of those, okay? And this is the type of data that we might want to use an Anova to test for. And in the week 4 assignment, I showed you how to do an Anova in Ggplot. And remember, in an Anova, analysis of variance, Anova is just the acronym for that, we're thinking about variation within these groups. So within the four-wheel drive vehicles, variation within front-wheel drive, variation within rear-wheel drive vehicles, and then among, how much difference is there between 4 versus front-wheel drive, 4 versus rear-wheel drive versus all of the pairwise comparisons, okay? And now we're thinking about, still we've got distributions of data, but now it's a distribution of a continuous variable, okay? And there's one more plot that is becoming relatively common. Instead of the old school box and whisker plots, I'm just going to triple click on line 41, right click, I'm going to copy, I'm going to paste that, but then I'm going to change the type of plot, and we're going to do geom underscore violin. And these violin plots are just another way of showing data that might be more intuitive if you're thinking about frequency distributions. Okay, so I'm going to run that. And notice these plots now, instead of box and whiskers, what it shows is a symmetrical plot. And each of these do kind of look like a violin. That's where the name violin plot comes from. And we really only need to think about half of this thing because it's totally symmetrical. But this is basically a frequency distribution turned on its side. So notice we've got a lot of data around this 13 to 14. Then there aren't very many observations. Then there's another little hump out here around 18 or 19, and then it goes down, okay? And so what we're really showing now are frequency distributions turned on their side and reflected, and then across those different categories. And this is a pretty powerful way of showing how the data that a box plot might just kind of throw into the box, how are those data actually distributed over this continuous variable city fuel economy, okay? So you might see these violin plots more and more often, and I think they might be a bit more intuitive than a box and whisker plot. So I just wanted to show you, this is again just kind of growing the foundation of the plots that you guys are familiar with. But a violin plot might be a better way of showing that. something that's easily implemented in Ggplot, but like when we were using Ggplot, we can't create these. And so, it's a little easier to stay on the cutting edge of showing data if you're using, something like Ggplot, where there's a lot of people that are working on creating cutting edge ways of showing data. Okay, and the Violin plot is just one of those that's kind of emerging as something that you might see. Okay, is everyone doing okay? No questions in the chat or hands raised, we can keep going. So let's think about some of the assumptions that would go into an Anova type test, okay? So if we wanted to test whether or not there were significant differences among four-wheel drive, front-wheel drive, and rear-wheel drive vehicles, considering their city fuel economy, an Anova might be the first test that comes to mind. That's the parametric way of asking about comparing means for more than two groups. If you only had two, you could do a t-test. If we have more than two, then we move into the world of an Anova, okay? But an Anova has some assumptions, just like linear regression does, regarding the distributions of data, including a normal distribution and the standardization of variances. So if you remember, we can test for or test for normal distribution in the response variable using this Shapiro test. Okay, so we can do Shapiro test and then MPG, and we just have to give it a vector of data. And in our case, we're thinking about city still, okay? And this was something that we did in the week 4. We just ran the Shapiro test. And remember, we get a test statistic and the p-value. And if the p-value is significant, what that means is that the distribution of data differs significantly from a normal distribution. And so if you remember back to our first pass at these data, we do have a distribution that is skewed. So we can test, and so remember, we're testing for normality. It's not a bell-shaped curve. Then we can do tests for kurtosis or skewness if we want to try to learn why it's not a normal distribution. But for today, we won't rehash that. We'll just kind of end with testing for a normal distribution. We can also test for homogeneity of variances, or the so-called homoscedasticity, as we talked about. And there, what we're thinking about is, within each of these groups, do we have the same range of data? And notice for front-wheel drive vehicles, the range of data, or the variation, the variances there around the mean may be different compared to a rear-wheel drive. Notice the truncation of just the distance along that gradient that exists here, okay? And we can test for, so Anna can take this and say test for homogeneity of variances, okay? And to do that, we're going to use the car package. So I'm going to do library CAR, okay? And I know this class is starting to look like I have an obsession with vehicles and cars, but those are just like the data that are helpful. That's why we're looking at MPG. And then CAR in this case is actually an acronym. Here it's Companion to Applied Regression. That's what CAR stands for. So this actually has nothing to do with vehicles. This is the Companion to Applied Regression. And if you have not installed that yet, you'll have to go to Tools, Install Packages, and then you can look on the CRAN for CAR, and there it is, CAR. Okay, and then you can install that. And remember, when you install a package, you only have to do that once. It downloads it and it puts it in your library on your machine in a local directory. So you don't have to have an internet connection after you install the package. You just have to be able to link to your library. But when you're installing a package for the first time, an internet connection to the CRAN is critical, okay? And CAR, Companion to Applied Regression, has a lot of dependency packages. And so it takes a little while for that one to load, okay? And you can notice there's a stop sign right here down in the console, and notice that little right-facing arrow in blue does not appear there. What that indicates is that R is still working on installing that package. If I decided I didn't want that package, I could click that stop sign and stop the process. But I'm not going to. I'm just going to allow that thing to run. But sometimes when you're running a very complex statistical model that takes R a little bit of time to implement, you might see the stop sign. And you might notice that there's no cursor down here to input more information. And that's because R is currently working on executing the previous line of code, okay? So that stop sign is something to keep an eye out for, okay? And this machine, I guess, is aging. It's kind of slow today, but this will give everyone else a little bit of time if you're following along, and I hope you are, to install the CAR package. And once it does install the companion to applied regression, there's a test there that allows us to assess this homogeneity of variances, also known as homoscedasticity. And remember from that lecture that I gave on Tuesday, if the variances are not homogeneous, if they're heterogeneous, then we call that heteroscedasticity, okay? And then we need to think about running a non-parametric model, okay? Because remember, Anova is parametric, but there's non-parametric equivalents of the Anova. And the way that it does that, by the way, I know this is not a stats class, but for a non-parametric, instead of the raw data, what it does is it ranks the observations. And then the non-parametric data will compare the ranks, okay? And so it's rescaling the data on ranks instead of the original city highway data. So that's why we can, when we violate these assumptions of homogeneous variances, if we do the non-parametric, we're doing a rank-based test, okay? So a little bit of stats background there. Are others installing this, and is it taking as long for others?
I think I'm having some trouble with mine.
Okay.
Yeah, like I tried loading it, and then it says loading required package car data.
Okay. Oh.
But it hasn't done anything besides that.
Okay. Caitlin, yours is taking a long time too. Okay. We'll give it a minute. This is one of the criticisms of these packages that do a lot of functions. See all of the packages that are loading on mine now? It has a huge number of dependent packages. And so when you first install it, it can be kind of a long process. We won't have to wait this long again. Okay, so I have just basically wiped this computer, so I don't have a lot of other packages loaded on here, and so you guys may have some of these that were loaded for other dependencies and other packages.
I don't have the stop sign.
Did it go? Yeah. Yep. Okay. Yeah. If it says loading required package car data, that means that it actually went on your machine much faster than my machine did. Yeah. So the stop sign should go away, and you should see the little blue right-facing arrow there. And that red text, I know red text is alarming, and some of you, it's like if you've wrestled with R, you're just tired of seeing red text. But red text is not always bad. If it says error, then it's usually bad. But if it's just red text, or sometimes it says warning, that's not always a failure. And sometimes it's just giving you information that may be of use or may not have been of use, okay? And so in this case, if the little bit of red text that you see there says loaded required package car data, is that what it says? I haven't gotten there yet on mine. Oh, there, I made it. Okay, so see, the stop sign went away, and we have this right-facing arrow. And so what that means is the console is ready to process more information. And so I can run library and loading required package, car data. It's thinking about it, and there it goes. Okay. So Caitlin and Adi, did it work out for you? Did you make it to this stage?
Yes, yeah, it went straight to that car data, so I guess it just loaded quickly.
Yeah, your computer's more powerful than mine. Everyone else doing okay?
Good.
Good. Okay. Cool. All right. I got the chat box here. Just let me know if you have issues. And of course, if it doesn't work, I'm happy to work outside of class with anyone. I would go ahead and download this one. This companion to applied regression is a very helpful package. And the reading, by the way, there's readings for each week, and we don't spend a lot of time on those readings. Those are mostly FYI. But for this week, there's an entire book on companion to applied regression that Fox has written. So that's like just like Ggplot. There's a lot more information out there that we can't cover. But those books are really great. Most of the time, what they have is code, examples, and screenshots of what it looks like, and so they can be really helpful for learning this stuff. Okay, so there's more information out there in that on the syllabus on Canvas. I give you a reference to a book devoted to car. Okay. Okay, so let's just we won't spend that much time today on car. We'll kind of learn about it as we go through the rest of the semester. But the test we're interested in is the Levine test. And notice when I type that in there, there's two. There's Levine.test, and then there's Levine test with the camel caps there. And notice that if I hover over the first one, they're both from the package car. But the first one says these functions were deprecated. And what deprecated means in our language is that that function has been replaced by another function. So it was deprecated in 2009, and it's now defunct. That means we don't want to use that one. What we want to use is Levine test with the camel cap on there. And now it says computes Levine's test for homogeneity of variances across groups, okay? So as you start to build your experiences with R, when you find functions from older versions, you may see this term deprecated. And what that means is that you can't use that function, but there's another one out there that has been created. And RStudio was helpful and found the more recent version of it, okay? So we want to use the Levine test with the capital T. And then we actually have to give it an equation, because what it's going to do is create something like this plot that we have down here. And so we want to tell it the response variable, which is in this case is CTY. And then we use this tilde sign, okay? And this is anytime you're dealing with equations in R, and as we move into regression, you're going to see this quite a bit. There's the response variable to the left of that, and then the predictor variable or the independent variable to the right, in our case, which is DRV. And then we just need to tell it where the data comes from. Data equals MPG. And when we run this, what I want you to notice is that this Levine test is going to automatically drive a factor for us, okay? So I'm going to run this. Okay, and I misspelled city, CTY, okay? So in the error was that it could not find that object, so I'll spell that correctly this time, and now I'll run it. Okay, and I got a warning message. So it says in Levine test default, and it tells us the arguments. Y is our response variable. Grouping factor is the predictor variable. And it says group coerced, and that D is just a continuation. Slide this over. Group coerced to a factor. What that means is it automatically created a factor for drive. And that's because I did not go in and create a factor for drive like I showed you how to do on week 4. An alternative would have been to use the word factor around drive. And if you do that, notice it runs the test and it doesn't give you that warning message. And so this is another case where the red text is not necessarily a bad thing. In this case, when we didn't create a factor for drive, it coerced it or transformed it to a factor for us. And then it went ahead and ran the test. And notice the output is the same between the two. Okay. So this is testing for homogeneity of variances, where it's looking for differences in the spread of the data between the three groups in our case. Okay. And notice that there's not a significant difference. We have our degrees of freedom. So for those that have spent a lot of time thinking about statistics, degrees of freedom is always n minus 1. And because we have three groups, an n of 3, n equals 3. So 3 minus 1 gives us 2. And then it gives us the total number of observations down there after the test. So those are our degrees of freedom. It gives us an F value. This is our test statistic. And then it gives us a P value. And what that means is there's no significant difference in the distribution of variances among these groups. So we actually do meet the assumption of standardized variances here. Even though this looks like it's much different than this one, when you calculate variance, there's only a few observations out here that are pretty much considered outliers. We do meet that assumption of standardized variance. Okay. So that's just one of the tests that you can do with the CAR package. Okay. So given that we meet the assumption of standardized variances, but not the assumption of normality, what that means is that we need to run a non-parametric test. And so I thought, for the purposes of just learning this stuff, I'll show you how to run an Anova, which we could run if the Shapiro test had shown that our data were normally distributed, and if the Levine test showed that the data have standardized variances. Okay, so just for the sake of doing it, just for comparison, let's run an Anova. Analysis of variance, you'll always see it as Anova, capital N-A-N-O-V-A. Okay, so we'll do test 1, T1, and we're going to do, there's two ways of doing Anovas. I'm going to show you both. T1 will be the first way, and T1 will be the second way of running an Anova in R. So the first way is a test called one-way.test, and this is from the stats package. One-way test, whether two or more samples from a normal distributions have the same means. And this one is interesting. The variances are not necessarily assumed to be equal. And so I wanted to show you this one in case you do violate that assumption of unequal variances. You can still run an Anova using this one-way.test. And you do the var.equals or var.equal equals false. And what that means is if the Levine test comes back as significant, you've got unequal variances, you can use the type 3 sums of squares instead of the type 1 sums of squares, and you can still run an Anova on that. Okay, so we're going to use the one-way.test. We're going to do CTY as our response. And then we're going to do DRV as the independent variable, or the grouping factor. Okay, so then we just need to tell it where the data comes from in PG. And then we're going to do var.equal equals true. The default is that they aren't. The default is to use the type 3 sums of squares, but we just ran the Levine test and we know that our variances among the groups are equal. So we can do equals capital T, or you can spell out true entirely. And that's a shortcut that they've recently implemented. You can just do the capital T, okay? Or spell out true, that's the same thing. Okay, so we're creating an object called T1. It's based on the function one-way.test. We're testing whether city fuel economy differs by the grouping factor drive from the data frame MPG. And we're going to tell it, instead of using the default of variances are equals false, we're going to change that to T, okay? And so if we run that, because I named it T1, it doesn't automatically give us the results of the test. We have to type in T1 to get that information. So I'm just going to type in T1, the object that we just created. And now it tells us the output of our one-way analysis of means, also known as a one-way analysis of variance or a one-way Anova. It gives us our F statistic or our test statistic, the numerator degrees of freedom, the denominator degrees of freedom, and then a p-value. And notice the p-value here is highly significant, shown in scientific annotation. And so what that means is that based on this analysis of variance, Anova, there is a difference there, okay? And of course, we would want to interpret that with caution, because when we test for whether or not the data were just normally distributed, we did find that they aren't normally distributed. But just for comparison, there's one way of running an Anova when you do make that assumption of normally distributed data, okay? Because I remember when I asked what test you guys want to learn, there was a few folks that said Anova, and there it is. Okay, let me show you the second way of running an Anova. Oops. So I'm going to go back up to the console here. I'm going to go T2 for test 2. And the other way of fitting an Anova is AOV, Analysis of Variance. Okay, and so AOV, we still give it a formula. We still tell it the data. There's some other functions or arguments within that function that we might use, but we'll just keep it simple for today. We'll use the function AOV. We'll do city as our response variable. So some of this stuff should be repetitive because we're using the basic structure that R uses for fitting these types of models. And then we'll just tell it where the data came from, MPG. Okay. So here, using the AOV function, everything else is the same. And this argument we don't use in the AOV function. Okay. We can run that, and one of the subtle differences is when you use the AOV function, you have to do summary of T2. Okay, we didn't have to do that when we use the one-way.test, but you do when you run the AOV. Okay. Now I realize those are nuances that there's no way you could have predicted. There's no way you could have known to do that, and that's where taking classes like this and learning those things is important. So now, for those of you that are interested in running or applying an Anova, you've got the code to do it. You just change your input data, you just change your response variable, and you just change your predictor variable. But the structure of the functions and the arguments doesn't change. Okay. If we look at the output from that one, we can compare it to what we got from using the one-way.test function. And they should be very similar, if not identical. Okay, the degrees of freedom and the F value are the same. The F statistic varied just slightly, but that's just they use different ways of rounding between those two. But it doesn't change your conclusions in any way. Okay. Is this going all right for those in the class interested in Anovas? So remember, we can use a t-test to compare just two groups if it's normally distributed data. And then if there's more than two groups, we use an Anova. But what we have concluded here so far using the Anova is that there are differences between at least two of these groups, but we don't know which are different from each other. And that's where post-hoc testing or pairwise differences comes in. And I just wanted to show the folks that are interested in Anovas how to do that. Okay, so we can annotate this and say determine pairwise differences. And to do that, there's a couple of ways. We'll start with the one that is most often used, and that's called the Tukey HSD. So Tukey was the inventor of the test. Honestly significant differences, Tukey HSD. And that's the function that we'll use here. And we can use that on T2. This model that we created here using AOV, we can run the Tukey's HSD to determine which of these groups are significantly different from each other. So it will do all of the pairwise comparisons. And it will account for what's referred to as experiment-wise error, or the fact that we're now doing multiple tests. So we're doing four-wheel drive versus front-wheel drive, four versus rear-wheel drive, and then rear-wheel drive versus front-wheel drive. That's 3 tests. The Anova was a single test. And experiment-wise error comes into play when you think about the fact that the more tests that you run, the more likely you are to find a significant difference. And so we want to control for that experiment-wise error, or inflation of the type 1 error rate. Remember, type 1 error is finding a significant difference when it doesn't exist. And then a type 2 error is not finding a significant difference when it does exist. So we're inflating the type 1 error rate by doing a whole bunch of tests, because we're more likely to find a significant difference if we do an infinite number of tests compared to a single test, right? So what this Tukey honestly significant differences will do is it adjusts the threshold for significance by taking the alpha 0.05 and dividing it by the number of tests that we're doing, which is 3. And so that's called a Bonferroni adjustment. And Tukey HSD does that automatically. Okay, so let me run that. I know this is kind of getting into the realm of statistics, and this might benefit some of you that are interested in running this stuff. And hopefully it's reinforcing the concepts for those that have spent time thinking about this. What it's showing is Tukey multiple comparisons of means, 95% family-wise confidence interval. So it shows us for front-wheel drive versus four-wheel drive, the average difference between those two is 5.6 miles per gallon. The lower confidence interval is 4.6. The upper is 6.6. And then it gives us the p-value. So there is a significant difference between front-wheel drive and four-wheel drive with the p-value there. And that's an adjusted p-value taking into account these multiple comparisons. But rear-wheel drive versus front-wheel drive, so or four-wheel drive, I mean. So this distribution versus this distribution, the difference is pretty small, and it overlaps 0 with the confidence intervals. And the p-value is 0.93, which is non-significant. What that means is between the group of vehicles that are four-wheel drive and those that are rear-wheel drive, there's no difference in the distribution of city fuel economy. Okay. And then the last three-way comparison is the rear-wheel drive versus front-wheel drive. Notice now that it's a negative difference, but it depends on what the baseline is. So it's rear-wheel drive versus front-wheel drive. We get a negative value. But the confidence intervals do not overlap 0, and the p-value is essentially 0. So there's a significant difference between R and F. Okay. Okay, there's a couple more things that I want to cover for those that are interested in this, because again, I want this class to be helpful for those of you that are testing your own data. We may just push the regression stuff to next week. We've got enough time, I think, to finish thinking about one more way of doing post-hoc tests. And then we need to do the non-parametric version of an Anova, okay? So let's just say an alternative pairwise method. And here, the reason I wanted to show you this is there is a shortcut for not having to always have to do data equals. If you're doing all of your tests on the same data set, one thing you can do is the attach function and then MPG. So we're going to attach MPG to the memory of the console. And what that means is anytime we give the name of a column, it's going to go to this attached data frame, which is now MPG, okay? So we can do attach, it's now attached, and we can do the pairwise .t.test. And notice that's from the stats package. And now we can tell it CTY as a function of drive, and we're going to do p.adjust method, and we'll tell it Bonferroni, B-O-N-F in quotations, okay? So, and because we attached MPG, we don't have to do the data equals MPG. We can just run the comparison, okay? And again, if you were curious about alternative ways of doing the adjustment, so we have talked about the Bonferroni, where the alpha threshold is divided by the number of tests. It turns out there's a lot of ways of addressing experiment-wise error, or this idea of inflation of the type 1 error rate. Bonferroni is one of the less conservative ways. And what that means is it adjusts alpha by the number of tests, but there are more, there are ways where there's a larger adjustment to the threshold for significance. Okay, so you could do question mark pairwise.t.test if you wanted to find out other ways of adjusting for this multiple comparisons. Okay, so we'll just run that. And the output that we get here looks a little different. Here we have 4, it's showing it as a matrix basically. So there's 4 and there's F and then there's F and there's R. So when we compare 4 to F, the p-value is less than 2 to the negative 16, right? It's very small. We can't compare F to F, so it just gives you a dash. When we compare 4 to R, we get a p-value of 1, which would mean no non-significant differences. And then we compare F to R, we get this very small p-value, okay? And then it tells you the p-value adjustment method was Bonferroni. Okay, and then a very critical question from Ashley is, how do I unattach that if I'm done with it? And the answer is detach, open and close. Detach, open, close, okay? And when you detach that, now we detach that from the memory of the console, and we are no longer married to that data set for all of the analyses that we want to do. Very good question, Ashley. Thinking one step ahead, I like it. Okay. So let's end today then by thinking about the non-parametric equivalent of an Anova and post-hoc test, okay? So most of you that are operating in the real world of applied statistics probably already recognize that these assumptions of parametric statistics are not always met. The data are messy, as a statistician might call them. And so then we want to do a non-parametric comparison of more than 2 means. And then to do this, you use the Kruskal-Wallis test. And if you're thinking to yourself, how would I have ever known that Kruskal-Wallis, where'd you pull that from? That's the whole point of that lecture that I gave you on Tuesday about which tests you'll run according to the violations of assumptions that your data have, okay? So Kruskal-Wallis is in that flow chart of tests, okay? And we're doing this, remember, because the distribution of the city fuel economy data are non-normal. And so we need to do this rank-based Kruskal-Wallis test instead of the Gaussian distribution test that Anova represents. Okay, and the Kruskal-Wallis test is just Kruskal.test, and that's in the stats package. Okay, so Kruskal.test, and then as you might imagine, we use the same formula, city as a function of drd. But because we detached MPG, we need to tell it data equals MPG, okay? I could have just not run the detach and I wouldn't have had to put that argument in there, okay? Now, we don't have drive as a factor. And so let's see if this will run it. And it did. It recognized that drive was a factor. I know that because our degrees of freedom is 2. So there's, remember, 3 drive types, 3 minus 1 gives you 2. In our Kruskal-Wallis test, Kruskal-Wallis chi-squared is the test statistic. And then there's the p-value there, which, so our determination didn't really differ. Our conclusion didn't really differ. We still know there's significant differences in city fuel economy among these drive types. We just used a more appropriate test now, okay? And so when your data are highly significant, like these are, which test you choose is less important than when you start to move towards being right on the threshold of significance. And that's where running the correct test is really critical for drawing the right conclusion, okay? And then, of course, when we run a non-parametric rank-based main effect test, in this case across the 3 levels, we want to use a non-parametric pairwise contrast. And so we'll, let me go back in here, and we'll do a quick annotation here, and we'll say non-parametric post-hoc test, or pairwise comparison. And we need to load a library for that, and that one is FSA. Okay, and if you have not, and this one, by the way, is not as complex as CAR. So we can go Tools, Install Packages, FSA, Install. There's a few little dependency packages there, but certainly not anything like CAR. Then we can do Library, SFA. Okay. And by the way, it says the following object is masked from package.car boot case. What that means is CAR and FSA both use an object or a function called boot case. And what it means is we're going to use the FSA implementation of that argument instead of the CAR implementation. And if we wanted to use the CAR implementation, what we want to do is remove the FSA package and just run the CAR version of it, okay? So you may see that when you're running, but today we're loading a bunch of what might be redundant packages because we're going through all of these parametric and non-parametric versions. But I just wanted to make a note of that. If you ever see that, what does it mean by that? It's because that object or that identifier is used in both of those packages. And it's masking the one from CAR and using the one from FSA, okay? And then the last little thing that we want to use then is what's called the done test. And done test from FSA. And notice that if we do this done.test with the two colons after it, we can find out much more information about that, but we want to just use the actual function, which will always give you the package that that function comes from. Okay, and by the way, the done test is in that flow chart, and we just do the same thing. City as a function of drive data, because we unattached it, is MPG, and then we just tell it our method that we want to use, and here Bonferroni is a lowercase bh, okay? And again, you could have never predicted that. The only way you could learn that is do question mark done test and learn about those arguments, okay? Or take a class like this one where I'll teach you to do it, and then you'll always have this code if you want to run non-parametric pairwise comparisons after you do a Kruskal-Wallis test, also known as the done test, okay? And if we run that, notice we get a warning sign. It's not always a bad thing. Here, it's telling us drive was coerced to a factor. Because I didn't put factor in front of drive there, it went ahead and transformed it anyway. And then it also tells us done 64 Kruskal-Wallis multiple comparison p-values. Oh, and this is the, sorry, I said Bonferroni. We're using this is not Bonferroni. We're using this, the Jimmy Hochberg test, okay? So that, and you know, you can learn more details about that by doing the question mark done test. But that's the most common implementation that's used. So that's why I chose that one, okay? So it does the same thing that we saw earlier when we did the Tukey HSD. It tells us the comparison. It gives us a test statistic. It gives us the unadjusted p-value, and then it gives us the adjusted p-value. And this adjusted p-value is the one that you would want to report because we're adjusting the p-value for these multiple comparisons that we did, okay? And it tells us basically the same thing. This one is 6 to the negative 24, so that's significant. This one is 7 to the negative 1, which would be 0.7. That is not significant. So again, R and four-wheel drive and rear-wheel drive, There's no significant difference there, even when we use a non-parametric test. And then front wheel drive and wheel drive, that's 2.9 to the negative 11th. That is okay. Okay, so we'll end it there for the day because I know you guys have other stuff going on outside of this class. Next week, I want to pick up regression. And I want to, I spent a lot of time on this today specifically because there are folks in the class that want to run Anovas and post-hoc tests or the non-parametric equivalent of those. I will post this code so you'll always have it, okay? And remember, you just gotta kind of know the basics of what are the data that go into that test. And then you change those data for your own in the future, okay? So we'll end it there unless there's any discussion points. We have deviated from the syllabus for a number of reasons this semester for so many already. We'll deviate from it again. On Tuesday, we'll come in and we'll start with some regression-based fitting regression models. So that's linear model, generalized linear model, additive models, generalized additive models, generalized linear mixed models, and generalized additive mixed models. I'm going to show you the code for those on Tuesday. And then on Thursday, I'm going to give you a coding assignment where you actually will spend more time typing on your own and thinking instead of just kind of following along what I'm doing. Okay? Does that sound all right to everyone?
Sounds good.
Oh, wait, hang on. Tuesday. No, thank you for bringing that up. Tuesday is Texas Independence Day. Yeah, and our power grid's not independent, but Texas once was independent from the United States. So I guess you get a day off for that. So we will not meet on Tuesday. Caitlin, thank you so much for remembering that. So we'll just come back on Thursday and we'll go over stats. Is everyone okay with that? Okay, cool. Thank you for bringing that up. So there's no assignment due this week, and I guess there won't be next week. What I'll do is I'll post this code from this week, so you have that and you can archive it. And then I'll go over regression, and then I'll have some kind of some coding challenges that we'll do next Thursday. Okay, so I'll show you how to do it, and then I'll kind of ask you to do it on your own in a slightly different way, just like we did on that week 4 coding assignment. Okay, very good. Have a good afternoon for those that got to go. I'll see you next Thursday.
Thank you.
Thanks.
Yep, thanks. Take care.
I did have one question, sorry.